class, and welcome particularly to Johannes. Johannes. How are you? Hope you are doing
Okay, how are you, sir?
great. Okay, so last time when we parted, we introduced the notion of householders method. And we know that householders method, the purpose of the householders method is to take a symmetric matrix and transform it into into a tri-diagonal matrix. That's the purpose of householder method. Take a symmetric matrix, perform the operation, that is the method, and then you transform it into tri-diagonal matrix. And once you have the tri-diagonal matrix, the next step should be to apply what? The QR. To apply the QR to that, you expect to obtain a diagonal matrix. But obviously, when you apply the QR, you don't get exactly a diagonal matrix. Not exactly. The off-diagonal entries will be nearly zero. They will not be exactly zero because of the round-off error. But still, you'll be able to, after a certain number of iterations, to see that, okay, the element along the diagonal are approximately the diagonal, the eigen the values. Okay, so what we are going to do now, since we went through the algorithm, the detail and everything, now we are going to use the algorithm and apply it to the current problem. The current problem, as you can see on your slide, we are going to apply it to this matrix. And if you look at the matrix, you see that the matrix is symmetric. If I draw a line here along the main diagonal, let me do this. If you see that if you draw a line like this, that's the diagonal. And then to see if it's symmetric, you draw a line like this. You see that those 2 points are the same, 1, 1. Another line like this, negative, negative 2. And another line like this. These 2 and that 2, you see same. Another line from this one to that one, you see, is the same. And finally, these 2 numbers are the same. So that's the transfer. You transfer like this, but you can check along the diagonal, take a line there, and then you take another line like this, like a cross. See if the 2 opposite points, this one and that point is the same. This one and that point is the same. This point and that, they are all the same. So that's how you check that the matrix is symmetric. Okay, so or you complete the transpose and see that the 2 are equal. So this is a symmetric matrix. Now we are going to perform the householder method by following this. Okay, because it's a 3 by 3 matrix, if you want to get the zeros, we can count. The first 0 is for the first column. The second 0 will be for the second column. and the last 0 will be, so we have a total of 3 operations, 3, each for the corresponding column. What did I even, yes. How many? No, we only have 2, sorry. Because we want a tridiagonal, not a diagonal. We want a tridiagonal. Tridiagonal means that you have this first diagonal. Let me do it again. Tridiagonal means that the only non-zeros will be this diagonal. Then the main diagonal. And finally, the super diagonal. Like that. So these will be the non-zeros. Now the zeros will be created in the first column, but below these 3 diagonals. So we will zero this 2, which obviously, because we will multiply to the left and to the right, so those 2 multiplication will also zero this. And then the second one will just be to zero this one, which simultaneously, because we have 2 multiplication, we will also zero that. So we have a total of 3 steps, 2 steps. First step is to zero in the first column, first row. Second will be second column, second row. So we will compute A1 and A2, just those 2. And to obtain H1, we need to compute, to compute A1, because we need A1 and A2. So to compute A1, we need H1, and to compute A2, we need H2. As we can see here in the algorithm. What is it? Okay. So this is H1, and this is our original A. Okay, we assume that the original A is A1, right? In that case, we compute A2 and A3. So we have a total of 2. Good. So we compute H1. And for that, we just need W, because remember that the knowledge of H is determined by the knowledge of W, right? Because remember that the H matrix is identity. Sorry. It's identity minus 2. This is where we define H here. Identity minus 2 W transpose. So if I know W, I know H. So that's why we compute each time. Okay. So we'll compute A2 and A3, assuming that the original A, the original matrix is A1. Okay, so let's do that. So we are going to use this algorithm. If you see the summary, we'll use this one, or which can be generalized here. Everything is summarized here. Here k starts from 2, but if you take let's see, if you take k equal to 1, we get this one. Okay, if I take k equal to 1, if I put 1 here, this will be negative sine A21, which is what we have here. K equal to 1, j will run from 1 plus 1 to n. And alpha squared jk will be alpha squared j1, because k is 1. Put it there. So you see that it gives us exactly the same formula there. Now what will be our r? In r, we are here. You see that this A, which you have already computed to see that this A21 will be exactly what we get here. A21 will be here. So you can see that this one and this one will be exactly the same. Okay, now W1. So you can see that from W1 up to WK, Y of that is set to 0. So if K is equal to 1, so if I put 1 here, we only have one W1, which is 0, exactly what we have there. Now, W2, starting from 2, W2 is this ratio. Now here, K is 1. So if I substitute 1 here, that would be W2. That would be that same A here, which is A21, minus alpha by 2R, exactly the same. And finally, we also have that. So it will be exactly the same. So this, in fact, this formula here will give you the A's and AK's and HK for K starting from 1 up to N minus 2. That's exactly the same formula that we can use. Right. And because we'll be computing from A2, because remember that A1 is the original. So we'll be computing from A2 up to AN minus 1. Right? Because we want a tridiagonal. A minus 1, remember, AN minus 1. In the case of a 3 by 3, N is 3, N minus 1 is 2. Right? Because remember we say we compute up to AN minus 1. So if N is 3, 3 minus 1 is 2. So we will compute A2. If I keep what is there, right? Okay, so let us go straight to the application. Okay, now in order to do the computation, I will leave this screen. I will leave this screen and go to a different one where we'll be able to write everything in detail. So that's what I will do now. So I will switch from that to this new screen. Okay, so this is the screen. But now let me quickly, which note is this? 20. Okay, let me see. See error. So I cannot even open the serial. What is going on here? Oh. But I don't know. Okay, let me see. Open. I don't know what happened. I can't see. Anyway, since I don't want to waste much time, okay, I'm going to use this this line. Unfortunately, I'll be using this slide. Okay, how's all this matter? Good. So the next thing that I will do, I will write I'll write the algorithm. I'll write the algorithm here. So try to recall what we want to achieve here. So we have A that we want to transform into A n minus 1, which is H n minus 2, H n minus 1, and we proceed, sorry, minus 3. Eh? And we decrease until we reach H1, and we repeat, because this is A, the original, which is our A1 here, and then we repeat the same. Here we have H1, H n minus 3, H n minus 2. Right. Okay, so that's what we want to construct. And each of this H key, it's the identity minus 2 W, I will call it WK transpose, where the WKs are defined as maybe my definition of the WK, it should be superscript. Like that. And this is what we'll be constructing. Because if I have H, I'm done. And for that, I need to construct the WKs. So the algorithm, in order to compute, I would just say here that for K, you start from 1, because I told you that this algorithm is true when K runs from 1 up to n minus 2, because we need n minus 2. That is the highest. Hn minus 2 is the highest H that will be constructing. You start from 1 up to, you can see here, H1 up to Hn minus 2. Right. Meaning that in the case of 3 by 3, we will construct H1 and H2. We got n minus 2, which is 3 minus 2, is what am I saying? We only construct H1, huh? Am I right? Let me repeat what I said. K from 1 to n minus 2. Okay, Great. So we know that in that we first compute alpha, because that is the first step here, alpha, which is negative sine of alpha, sorry, A, those are the entries, A, of course, if we call that K, that's the iteration number, order, the kth iteration, and this is K plus 1, comma, K. So that entry, and then here we have the sum J. Okay, this one during the test or whatsoever, this formula will be given to you because I don't expect any of you to memorize this formula or to know it. It's really long and complicated. So you are expected to know how to use it to solve the problem. You are not expected to know the formula. So if this is asked in a test or whatsoever, the formula will be given to you. I hope it's clear. This formula will be given, right? It comes during a test or, yeah, a test. Since we don't have exam, if it comes during a test, the formula will be given to you. This one particularly, but for the other one, Jacobi, it will not be given, right? Jacobi is, once you understand the principle, you don't need to know any formula, you just apply the technique. But this one, you need to know the formula and it will be given. If asked, it will be given. So don't try to memorize it, just try to understand how to apply the formula. So J will run from K plus 1 up to N. And here we have alpha, not alpha because we are still computing alpha, that is A, those are the entries, A, J, K, the entries of the, that is square, right, A, J, K square. Where A is the entry. In fact, this A is exactly the same as this one. Right. But we are in the first column. This is the first column. Oh, sorry, the kth column. If I compute for the first time, it will be the first column. But if K, of course, that's when K is equal to 1, first column. If K is equal to 2, second column. So this is the column of that entry. So this A should be AK squared. So this should carry the K to indicate the order, right? Because remember that all these are the order here. So let me erase this to indicate that it's A2 squared. Because each entry here is denoted with a K. Okay, square. Great. And then we take the square root of that entry. Okay, once alpha is computed, the rest becomes easy because we need R. That will be the next step. R is the square root of 1/2 alpha square. You see that you need this alpha to compute R. That's why in that order you first compute alpha, and then 1/2 alpha square minus 1/2 A K like this, K plus 1 K. That is this same entry, right? Times alpha. And then we take the square root of that quantity and all the W's, all the WK, that is from the first entry up to the kth entry, are set to 0. Sorry, K. So if you remember, when k is equal to 1, we take W1 to be 0, and the rest we compute them. That's when k is equal to 1. So if k is equal to 5, we will take W1, W2, W3 up to W5 equal to 0, and then the rest will be computing. So that's what this means. So we set all of them to 0, and then we compute the remaining entries of W. Now that's to maintain, the purpose of doing this is to maintain the previously computed entries in the matrix. If you don't set them to 0, when we'll be performing the multiplication, it will go and alter or modify the previously computed entries in the matrix. I will explain that in the process, but I explained it last time, but I will repeat. That's why we need to put this 0. I explained that last time. Because remember that when we construct our age, we have identity whose entry in the column is already 1. Now we modify by subtracting 2 W transpose. So if these entries is not 0, for instance, for W1, the first time, if W1 is non-zero, when we compute that entry of W1, which will affect the first entry of the identity, like this, it will come and affect that entry in such a way that when we will be multiplying h by a, because remember we multiply the h with a, if in a we created already, let's say, a non-zero here, a non-zero there, and the rest is zeros, if I don't keep this identity, when I will multiply, it will come and modify maybe this entry, but I want that entry to be kept. Similarly, when I move to the second position, I want this entry to be kept. So that's why I'll also maintain this 0 and create a 0 in the entry of W so that it will not come and modify this entry. I hope you understand. Okay. So that is important to understand. So that's why we create those zeros in the W, so that when we multiply h, the new h, with the previously computed AK, it will not modify the zeros already created and the non-zeros already there, because we want to keep those exactly the same. The previously computed column should not be modified, they should be the same. And we'll just be modifying the subsequent columns, and we maintain the previously computed. In the process, I will indicate. I will indicate what is being done, so that the concept will be really clear to you. Because if you don't understand why we are doing some of these things, you will not be able to do much with this algorithm. And even design new method, because in order to design a new method, you need to understand how previous methods were designed, right? Because that's what inspires you to k plus 1 comma k minus alpha by 2r. And the other entries of W, because this is just WKK, k plus 1, I mean. Now the WJ, this will be AK, J, K by 2R. And this is for J running from k plus 2 up to n. So for a given k fixed, this W will be WK plus 1, k plus 1. And then k plus 1 is different from k plus 2, k plus 3 up to n. You see that they're computed separately. And finally, we update because we want the W's. So this is where we compute all our W's. Right, of course, from here, you know that these are 0 and the rest are this. So once these W are computed, the next thing is to compute H. After that, we can compute HK. Yes. That's why we need to identity minus 2 WK and the transpose. Yeah. And finally, we compute the A. So A, k plus 1 will be HK. This previously computed HK into A K and HK again. Don't forget that this one is actually the transpose, but the transpose is the same as H transpose is H. So that's why we don't put the transpose here anymore. Because for similarity, we need H or a matrix here, A and its inverse, and which is the same as H inverse because it's orthogonal, right? That's similarity, they are similar. So this HK plus 1 and AK plus 1 and AK are similar matrices. So that's why the eigenvalue that we obtain will be equal to the eigenvalues of the original because they are all similar, right? You should not lose that in mind. You should bear that in mind. You should not lose that focus. We are constructing similar matrices, knowing that if matrices are similar, they have the same eigenvalue. Good. So this is the algorithm, and we can end our algorithm at this level. So we end it here. Good. Now, application. We are going to follow this and apply it to this. So application is the example in class. Okay, so our matrix A is a symmetric matrix. So the entries of A are 4, 1, 4, 1, negative 2, 2. And the next is 1, 2, 0, 1. Now, because it has to be symmetric, this should be negative 2, as I explained. This is 0. This is 3. We have negative 2 here. So if you take, no. It's 4 by 4. 1, 2, 3, 4. 1, 2, 3. Okay, the last one, it should be this 2. Because this column is that row. If I take this, I repeat it there. That is 4, 1, negative 2, and then 2. This one. Right. And then by symmetry, this should be 1. That's 2, 1. Two, 1, and this -2 should be here by symmetry like that. And then we have the last entry here, which is -1. So we can see that the symmetry, if I do this, this, we should have symmetry, and also this. So that's the symmetry. So this is symmetric, symmetry. Okay, so our H1, A1 is A, right? A1 is already A. That's obvious, that's A1. Now we are going to construct A2. This is what we want to construct. And in order to construct A2, we look at the algorithm. And in the algorithm, remember that the first step is to compute alpha here. That's our first step. Because we need, and in order, of course, this is H. This is H1. A1, which is A. So what is this? H1. So that's what we want to get. And for that, we go into our algorithm. We say K is equal to 1. For K equal to 1 in the algorithm, what is my alpha? Remember, it's negative sign of what? A what? K plus 1, 1. So K is 1. So it will be 2, 1, right? Two, 1. Obviously, this 1 here on top is for this A. Remember, all the entries of A are superscripted with 1. So A121 is here. This is A1, right? 21, second row, first column, 1, 2, and it's this entry. Because we will keep this one, keep this entry, and 0 all the entry below that. So all the entry below this entry are those that we are zeroing. So we fix this one, we fix this, fix. Okay, let me put it here. We fix. And because we are tridiagonal, remember, tridiagonal means this should be 0. This 2 should be 0. And automatically, because we multiply on both sides, you also 0 this one. So that's the first step when we say K equal to 1. K equal to 1, we construct this. So it will 0 these elements when K is equal to 1. These are the elements that will be 0. So that's for K equal to 1. I will leave that in red. For K equal to 1. Right. Good. So that is alpha. And now we need also the summation, right? In our algorithm, there is a summation inside. Here, we have the summation of those A. Now, J's, remember, K plus 1. K plus 1 is 2. So K is 1 plus 1 is 2. 2N, N is 3. Now we have AJK. So J is K is 1. Like this, and then we take the square root of that. Right. So what does that mean? I take all the elements in the first column here, starting from the second entry here, that position. This is 1, 2. So I will take from this second position, the point that I fixed this point. That's what I'm fixing. I will start from this downward, right? It's square, sorry, here, square, A1 square, square. So I will sum this. Now, if I sum this 1 square plus 4 plus 4, right, that's 9. Square root of 9 is 3. So all this will be 3, right? And this A21 is this point is positive, so it will be negative 3. Is that clear? Is it clear that negative 3? Okay, if you don't understand, let me know. Now for R, we use the same formula. We know that R is what? Square root of 1/2. 1/2 of what? Of this alpha square. 1/2 alpha square. Yeah, 1/2 alpha square minus 1/2. Let's write it. Minus 1/2 this entry A 1 2 1 into alpha, and we take the square root. So what is that? 1/2 negative 3 square minus 1/2, that entry is 1, into alpha negative 3. And we take the square root of that. So what is this? This is 9, right? And this is positive with this negative. Negative, negative, positive. So that will be 9 plus 3 plus 9, which is 12. By 2, it is 6, and square root of 6, right? All right, good. So that is it for this point. Now we compute our W. Remember that in our W, we set W0 to W1 to 0, the first entry, W1. Because remember for K is 1. K is 1. Every entries in W up to WK should be 0. So every W up to W1 should be 0, but since it starts from W1, only W1 is 0. So I know already that I can write here WK, which is W1, is 0. So this implies that W, the vector, I can already set this to 0, that first entry. Now I have the remaining entries that I need to compute. Now, so that's W2, W3. Okay, now how do I compute W2? Because that's what I need. I already have alpha and R. Since I have alpha and R, it becomes easy. So what is W2? And this is what? 2 is K plus 1, right? So WK plus 1, in fact, let me write it here. This is WK K plus 1, and here we are K, right? So this one, WK plus 1. Remember, because we have WK plus 1, which is different from WK, where the substitute start from K plus 2. They are different. So we will take the entry, the fixed entry minus alpha by 2R. So this will be, in our case, this point, the fixed point, A 2,1 minus alpha by 2R. And what is that? The fixed point there that I mentioned is, what is that value? Is 1. So that would be 1 minus alpha, which is this, by 2R, that's 2 square root of 6. And what is this? So this is 4. 4 we divide with this one, with the 2, is 2 square root of 6. 2 square root of 6 is the same as, if I multiply the numerator and the denominator by square root of 6, the denominator becomes 6, with the 2 here above will be 3, so that is square root of 6 by 3. All right, so we have that entry. That's for W2. Now W3, what is W3? Remember that this W3, we have this formula, and 3 is in fact n, right? It will be this same entry by 2R. So we remove the alpha. We just remove this alpha from the above. You can remember it, you just remove the alpha and you get the result. So if you remove this alpha, you see that it's 1 by 2 square root of 6. 1 by 2 square root of 6. And what is that? It will be square root of 6 by, and multiply there. Square root of 6 by what? What did I say? I say we remove that. Okay, sorry. It's not the same, but you have J here, sorry. You remove the alpha, but this one, because this subscript is K plus 1, right? It should be J. Okay, so it is the same, but the corresponding entry with 3. So meaning that it is the element below this. We move below the first column. So this is changing. Now that W3 means that the third row. So what is the third row? 1, 2, 3. So that element below, and the next one will be element below, and so forth. So this element is -2. So this is -2. So you can see that it gives us that is -1 by square root of which is negative square root of 6 by 6. And do we need to compute any other entry? This is W3. Oh, W3, we still need another one. It's a 4 by 4 matrix. So, okay. So the next one, we will take the element below this entry, which will be 2. This one, the next one. Okay, so we can see that similarly. Now, W4, you just take that entry below, which is 2, by 2 square root of 6. And that gives us 1 by square root of 6, which is equal to square root of 6 by 6. Now, with this one, all right, so we conclude on our W. So W, the first entry is 0. The next one, we saw that the next one was square root of 6 by 3. Square root of 6 by 3, and then negative square root of 6 by 6, square root of 6 by 6 transpose. So this is our W. Now to construct H1, of course, this is our W1. That is when K is equal to 1, because we fix K to be 1. Right. Obviously, these are the entries. I don't need to put the, in fact, if I want, I can still put the superscript here, right? But it's fine. I still leave it. Okay, so that's our W1. Now, our H1, we know that H1 is the identity for, that is because we are in R4, minus 2 W1 transpose. This is a matrix, so we need to form that matrix. So we compute our H1, which is we take the 4 by 4 identity, 1, 2, okay, I don't want to write a very big identity. Let me just put it like this. 1, 2, 3. 1, 1, 2, 3, 4, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, so this one is like this. Okay, so that's the identity. Now, minus 2, that, this times that. Now, you can see that I have a common factor here, square root of 6 by 3. I can factor it out. Actually, even this one, I can factor even this one, because I can write this to be 2 here and 2 there on top. You see, 2 into that, and then I factor this so that I will not manipulate too much terms. So I have that expression in this one and in the transpose. I have it here and in the transpose. So I will factor it on both sides. Then I will get here square root of 6 by 6 squared, because I factored this in W1 and in W1 transpose. I will take it 2 times, so we square. Okay, so if I do that now for W1, which is a column vector, because remember when we write this is a column vector, right? A vector is a column vector. So we have a column vector here. And then we have the first entry here, which is 0. Remember, we factor square root of 6 by 6. So here is 2, right? So this is 6. And then you have this 2. Then we have negative 1 and 1. Negative 1 and 1. So this. And since this is same, now when we transpose this, it becomes a row vector. So 0, 2, -1, 1. Okay, now is it a matrix? Yes. Why? Let me check. If it's a matrix, this is a 4 by 1. So this is 4 by 1 times the 1 by 4. You see that when you have something like this, cancel this, and the size will be this. So that is a 4 by 4 matrix. Good, so that's what we have. Now, the computation, we already exceeded time. Do you have a class after this? Do you have a class after this? Or I should, okay, let me then proceed and finish this example. Okay, explanation is really important. Okay, those who can leave, please leave, and you can download the video later on. Huh? I really need to finish this example. Okay, so that is a 4 by 4 matrix. Now, what is this? So that this will be equal. I can repeat this. Okay, let me quickly repeat that. It will not, anyway, I will not waste time. I will just copy this. Right, good. Now, this multiplication, I will write it here to make things easy, right? So, sorry. So here I have a 4 by 4 matrix. That I'm going to compute. So this is a 4 by 4 matrix made of this. Okay, now I'm going to compute these entries in the first column. When I say first column here, this will be for the rows, right? Remember, the first matrix, you take the rows and you take the column in the second. Now, if I say first column, it means that I fix this and I vary the rows. And now, if this is fixed, you agree with me that all the entries here will be 0, right? Because this, as a column, is fixed. And I will be multiplying each row with this 0. So if I multiply each row with this 0, everything will be 0. So we have 0, 0, 0, 0. That's the first column. Now, the second row is this one. Sorry, the second column is this one. So I will take that and I will multiply each entry here, and that will give me the row. So I will take this, multiply each entry. So that will be 0, 4, -2, 2, right? Similarly, I take this, multiply all that, that will be my third column. So I will just negate all the entries. So you have 0, -2, 1, -1. And finally, this one, I repeat, I copy 0, 2, -1, 1. So these are the entries of this product. Obviously, if I simplify this expression, let me quickly simplify. So all this expression, what is it? This is 6, and this is 36. Now, if I divide 36 by 2, because this one will be 18, right? Right? Because this is 2 times 18. Okay, so if I simplify this, I cancel this one. So this will be 6 by 18. And that is 1 by 3. You agree with me? Because this is 3 times 6. All right. So that will be 1/3. So all this is 1/3. So I'm done. What I will do, you remember, what I will do here, because I will be adding this identity to this matrix. So this negative 1/3 multiply all these entries, right? Multiply all these entries. Okay, so let me do that step by step to avoid confusion. So step by step, this is equal to, I will copy the identities. So we have the identity there. Now we say plus. Now this is negative, 1/3. So I will multiply all the entries. Obviously, these zeros here in the first column and first row remain 0 because I will be multiplying. So we have 1, 2, 3, 4. They remain 0. 1, that's 3, and then 4. So this remains 0. Now this negative, So I will negate all the entries and I will divide them by 3. So I negate and divide by 3. So this will be negative 4, 3, 2 by 3, negative 2 by 3. And this will be 2 by 3, negative 1 by 3, 1 by 3, negative 2 by 3, 1 by 3, one, 2, 3, negative 1 by 3. Good. Now, if I add them together, what do I have? Adding them together means that I will only add 1 to the diagonal element. That's all. So I will keep this and add 1 to the diagonal element. Right. So I'll add 1 to the diagonal element here. So this will be 1. Right. Diagonal element, so this becomes 5 because I'm adding 1. Oh, no, sorry. What did I say? 5. So I'll be adding 1 to this. Okay, this second one, I add to this one. So that will be negative 1 by 3, right? Because I will just take this minus there. Give me my negative 1 by 3. So this is negative 1 by 3 for this entry. And the remaining elements are the same. This is 2 by 3, negative 2 by 3. Right. And this is 2 by 3, negative 2 by 3. Okay, now this is another diagonal element. And since it's a diagonal element, I will add 1 to it. And then it will be 2 by 3. So this will be 2 by 3. So this remains the same, 1 by 3. 1 by 3. And since I think this is okay, it's the same. That is 2 by 3. Okay, so that is how we obtain that entry. In the note, you just see the result, but you don't see the complication of the computations, right? Okay, so that's how you obtain H1. You see, it's computationally intensive. You come in. Okay. Not now, I have a class. Okay, so that this is H1. Now, if you check, let's check if there's any error with the result in the notes. So you have this one, you have that, you have this, you have that, you have that, you have this, you have here, you have, it's exactly the same. It's exactly the same as in the note, no different. So, oh, sorry, so this is correct, after checking. Correct. Right, so what is the next step now? We have A1, which is A. Now, what is A2? A2, because we have H1. So, now we have our A2. Is H1, A1, which is A, H1. So, do the computation yourself. I'll just use the result. You'll be able to get that. That's 2 matrix multiplication. I mean, 3 matrix multiplication. You first multiply by, you can first multiply these 2 or those 2. The order is not important. And you get this result for -3, 0, 0. You can see that these 2 are 0, right? And here you have -3, 10 by 3, 1, 4 by 3. Obviously, here you have 0, 0 by symmetry, right? Because you multiply also each here, you 0 this 2. And then this entry is 1. And this diagonal element is 5 by 3. And this is -4 by 3. And then here you have 4 by 3. -4 by 3. And finally, -1. So you see that these entries have been 0, and that's what we wanted. Right. So the last step is k equal to 2. Because remember, we say we go up to n minus 1, right? N minus 1, which is 2. You can see it from here. Here, n minus 1. We will compute up to n minus 1, which is Wait. There's something. What we have just computed is A2. This is K plus 1. N minus 1, because now we are computing A3. That's for K, huh? K. That's for K. This is AK. That's for K. It doesn't work here. This K if you do that, you know that the number of times that we zero, you have 1 and 2, which is n minus 1, right? The number of computation, it will be 2. So this is the first when K is 1 and then 2. So it doesn't, it's a bit confusing if you apply it that way. Okay. So we have that. Okay, so the last step now. The last step is this one. Now we want to, let me use a different color. Maybe the green or the magenta. Okay, magenta. This. Okay, so this is what we want to zero now. Okay, that entry. Sorry, I'm in a class. Okay, so yeah. Okay, so I was talking about this point. So K equal to 2. Yeah, that phone call really distracted me. Okay, so K equal to 2 now, which is the last one, because this is n minus 1 I was talking about. And that's the last. So if you have a n by n, K will run from 0, 1, 2, 3, up to n minus 1, so that we get a tridiagonal. Okay. We just repeat the process. Remember that now K is 2, right? Now, remember that the A that we take is AK, K for the order of the matrix, because our AK now is A2. AK is A2. And all the entries of this are A2, let's say IJ if you want. IJ. Right. That is the K, right? When you say we put the K here, it corresponds to the order of the matrix. When you say order, that is iteration order of the matrix. A2, this one that we computed, this is A2. So all these entries are A2. Right. Now, to compute the alpha here, remember we have negative sign of A, K, the entries. Now here we have K plus 1, comma K. Good. Now because K is 2, K plus 1 will be the next column corresponding to K equal to 2. So if K equal to 2, when you say K plus 1, of course, the column is K. K here is the column. That is the second column. We are in the second column, which is this column here. The column where we want to zero the entry. So we want to zero here in the second column. K equal to 2. That is the key. Second column here. So we are here. Now, the entry, that is the row, is K plus 1. That is the third row. Because remember, we always move below the main diagonal. Because this is the main diagonal, we fix the element below the main diagonal. Similarly here, this is the main diagonal, we fix this element because we don't want to disturb it, we don't want to zero it, that's why we fix it. If you remember what I said previously, that we fixed an element, here it's -3. Let us go up again and check. We fix this entry. This is the entry that we don't want to perturb. We fix this entry. Now, when we compute, you see, it gives us -3 here. But it remains a non-zero entry. We don't disturb that one. It's non-zero. We zero what is below. Similarly, we will fix this entry. We will not disturb it, but when we multiply, it will be modified. But this column, this entire column, will not be changed. This entire column for -3, when we compute A3, you will see that -3 for -3 will be the same. If you check even from the note, you see that that entry remains unchanged. For -3 remain unchanged. That one we don't. So we fix this point, and this point that we are fixing is that entry. So this is the point that we are fixing. Let me frame it, box it in blue. So this is the one that we fix this point, and that's what we use here in all our computation. Our A, K plus 1, comma K will be that point that we fix. That's what we use in our algorithm. And now we just use the summation here. Of course, it's the square root of that entry. So we take this, we take those entries, take that summation, square. So we take A, that is 2, right? A to J, the same J here. That's here's K plus 1, that's 3 to 3, right? And now we have J and then the column, which is 2. We square it and we take the square root. So this square and then square root of that. So that is that okay, then this is 1, so the sign will be -1. So this is negative. Now, if we square all these entries, because second we are here, and we start from 3. 1, 2, 3. We start from here, and we square. So it will be 1 square plus 4 by 3 square, and we take the square root of that quantity. That is 1 plus 16 by 9 square root of that. So now 16 plus 9, because I will do that, that is 25, right? Now if I take the square root, this will be 5 by 3. So this is -5 by 3. So that is how you get this alpha, and you compute the rest. Let me. Good. So that is your alpha, -5/3. And similarly, you compute your W. I will not do that. It's, you know already. W, which is W2. Remember, we zero all the entries up to K. K is 2. 0, sorry, this is 1, and this is 2. So all the W up to K, which is 2. So 1, 2 is 0. Now the remaining ones are the ones that we compute. So we have already 0, 0 there. So the computation, I will put that in red, that you have to compute it yourself to see that you get this. And then square root of 5/2 by 5. This one you can compute because I gave you I already performed the computations. Now you know how to do that, and you compute the matrix H2 exactly the same way we proceeded here. You follow all that, and you will get that H2 just using the result. This will be 1 and then 0, 0, 0, right? And then 0, 1 here. And why are we having this? You see that this is because we want to preserve the first column. You see that this is, you have that. So when we multiply, this first column will be preserved. It will be unchanged. And similarly, this first row will be preserved. It will not be changed. So that's exactly what we are trying to do when we fix, we have that. And the other entries, so we have 0 here, 0 here, 0, 0, and then we have -3, 5, -4, 5 by 5, of course. And here it's -4 by 5. And finally, 3 by 5. Okay, so with this one, we can compute our A3, which is H3 into A2 H3. And the result is the following. So you see that when we multiply this, that column, first row, will remain unchanged. So A3, you get 4, -3. The 2 0 that we zero are here. And this -3 is here with the 2 zeros. So you can see that these are unchanged. Unchanged. They are fixed. Unchanged. Okay, so the new entries, obviously this also 10 by 3 is unchanged. This 10 by 3 is unchanged. And why is it unchanged? Because of this one, right? Because of that. So this entry here is unchanged. The same way, when we computed A1 from A, you can see that this 4 was unchanged. That 4 was unchanged. Right? This 4 was unchanged. So that's what we have here. That 4 is unchanged. So when we proceed, this -3 also will be unchanged, because these are the values that are next to the entry in the diagonal here. Okay, so they remain unchanged here, and this element which is on top of the element that we are fixing, because we fix 1. We fix 1 here. The element that is on top of it is unchanged. This is the one that we fixed. The element on top is unchanged. Now, here we fix 1. The element on top of that one that we fixed is unchanged. And the off diagonal from that position are also unchanged. So these will be unchanged. And you have that here, and this is fixed. Okay, those are some of the remarks that are necessary to mention. And now here we have -5, 3. We have 0 and -5, 3 here. 0. Because of symmetry, you have to get that information to make sure that your results are not wrong. Now here we have -33 by 25, and here we have 68 by 75, which is the same that will be here, 68 by 75. And finally, this entry, 149 by 75. Okay, so that's what you will get when you perform the computation. Now you can see that it's tridiagonal. Right? You have this diagonal, and that diagonal. Okay, so that is it. I will stop here, but I will record another video on the Jacobi, and that will be the end of the semester. But we'll stop here for today because of time constraint. Some of you, some of you will be having other classes to attend. So I will stop here for today. And I encourage you to watch the next video that I will record. I'm still busy with the script, so I will quickly continue the marking. So I don't know exactly. I'll be attending another meeting this evening. Unfortunately, I'll be attending a meeting. And latest by tomorrow morning, I will check the ITN or even the e-learning platform for the result. Anyway, I will inform the class representative to post the information on the e-learning. On your WhatsApp group when the results are released, so that you quickly check to see whether you'll be writing the makeup test or the supplementary test on Friday or not. It will be Friday evening from 5:15. That is 5:15 p.m. Okay, on this note, thank you for your kind attention. God bless you. And see you in the next video, in the next recording, which will be surely, if not during the course of the day, because if I'm done with the marking, I will just quickly record, or after the meeting that I will be attending. But by the end of the day, I will have to record something on the Jacobi method. It is easier for you to compute. For those who will be writing the test, if I give something on the Jacobi, it will be something simple that you can easily compute and get the result and get marks. So that's why I'm insisting, if I can do that for you to go through and understand how it works, because it will give you marks. It will easily give you marks for those who will be writing the supplementary. Okay, thank you. Bye. But you can read it, please. You can read the notes. They are already there in the note. Read the note and try to do the example at the end there. That matrix, try to solve and try to make sure that you can do that. You already have the notes. Please, you can do that. Try to read and make sure you can solve that problem while waiting for the video, because the video will just explain what is already in the note. It will be nothing new. There will be nothing new. Read the note, please, to prepare for the supplementary. Thank you.